Individuals with visual impairments face numerous challenges when using their hands to navigate. The lack of spatial awareness in particular can make it challenging for such individuals to have a clear sense of where objects are located in relation to their bodies, which can impact their ability to perform various everyday tasks. Most visual accessibility solutions use cameras mounted on smartphones or glasses to track the user's hand and the target object. Once tracked, these systems provide audio or haptic feedback-based guidance to the user to direct their hands towards the object. These type of audio and haptic feedback-based guidance systems have been the status quo in visual accessibility solutions for quite some time now. However, while these systems are effective, they rely heavily on the user's ability to interpret and act upon the received auditory and haptic feedback, requiring the user to manually move their hands towards the target. This manual interpretation and execution of the directional cues can involve significant cognitive processing, which can in turn increase the user's mental load. Now, let's recap how typical visual accessibility solutions work. First, the user's hand is tracked. Second, the target object is tracked. And third, audio or haptic feedback-based directional cues are provided to the user so that they may move their hand towards the target object. Now, we ask the question, what if there was no need for this manual interpretation and execution of directional cues? What if the user's hand just magically moved towards the target object? In this work, we achieve this by simply swapping the directional cues with hand actuation. So, once the system tracks everything, the user's hand can be actuated towards the target object. We call this as automated hand-based spatial guidance. Now, the hand can be actuated in many different ways. One can use electrical muscle stimulation to control their hands, or they can even wear exoskeletons. In our work, we achieve automated hand-based spatial guidance using FingerOver, an on-finger miniature robot. FingerOver is capable of moving on a horizontal planar surface, carrying the user's hand along with it. Users can simply rest their finger on top of FingerOver and follow its movement to reach their desired target. Automated hand-based spatial guidance can support a diverse range of applications for individuals with visual impairments. In our study with 7 such individuals, we tested the efficacy of our technique across 4 common accessibility problems. Spatial guidance can allow users to locate objects on a surface. Once the user chooses an object, FingerOver moves towards the selected object, carrying the user's hand along with it. Spatial guidance can also allow users to operate inaccessible touchscreens. To support this, FingerOver has an additional touchscreen tapper which allows users to make risk-free selections on the touchscreen. Spatial guidance can be used to remotely assist users in assembling objects with otherwise inaccessible instructions. In this example, FingerOver not only carries the user's hand to the object pieces, but also to where it needs to be assembled. Lastly, spatial guidance can also enable sense-making. In this example, FingerOver traces the triangle through its movement, thus conveying the triangle's shape information to the user. Our user study revealed several benefits of automated hand-based spatial guidance. Both blind and low vision participants were able to easily adapt to spatial guidance and found the technique to be effective in aiding them with the given tasks. Participants also highlighted that it was generally easier to follow along with the spatial guidance as compared to audio feedback. Despite FingerOver's slow movement speed, when compared to audio guidance, participants found spatial guidance to be more efficient in the tasks of operating touchscreen and locating objects. This could indicate that direct spatial manipulation of the hand allows for more accurate guidance. And while spatial guidance was not as efficient as audio guidance for the task of assembling objects, participants acknowledged that it might be because of the nature of the object used in that particular task, and also pointed out the value that spatial guidance can bring in more complicated object assembly tasks with smaller pieces and where verbal instructions are unclear. Finally, we observed that different participants had different spatial thresholds for moving their hands when following the audio feedback. So, while some participants made minute changes to their hands, others made drastic movements. Spatial guidance brought a uniformity to the entire process, where the participants' hand positions were tethered to that of FingerOver's. We acknowledge that FingerOver is not the most optimal way of achieving automated hand-based spatial guidance. FingerOver has several limitations. It has a very slow movement speed, and its movement is limited to horizontal surfaces only. Furthermore, FingerOver is only able to provide spatial guidance on a macro scale, not particularly ideal for finer interactions. Alternative implementation techniques, such as electrical muscle stimulation, for instance, can provide a far more intricate control over the user's arm, thereby allowing for more finer interactions and application scenarios. However, our design for fingerover was motivated heavily with user agency in mind. While the idea of automated hand-based spatial guidance is promising, the susceptibility of this technique to potential risks must not be overlooked. Since this technique takes the burden of controlling the user's hand off the user may relax their agency as they build trust with the system. And things can get really dangerous if the system gets compromised. Thus, safety must be carefully considered when implementing automated hand-based spatial guidance. In our study, users unanimously agreed that they felt completely in control over fingerover, and that they could stop following the spatial guidance at any point by simply lifting their fingers. Fingerover as a device is not strong enough to override the user's agency. However, this might not be the case with other implementation techniques, and thus special attention needs to be directed towards agency overriding mechanisms. We believe that automated hand-based spatial guidance has the potential to significantly enrich the interactive capabilities of individuals with visual impairments, and we would like to implore designers to consider this spatial guidance alongside audio and haptic feedback when designing solutions for such individuals. We invite you to read our paper to learn more about our work. Thank you for listening.
Please press the robot button.
Oh my God, this is so cool. What I found difficult was I really had to use good listening skills in it. And so I did get a little mentally tired from really having to concentrate. Yeah, it took off some of the pressure to listen as intensely as I had to for just the audio.
Because it's so laborious to go through all the stuff they got to go through.
Right.
And this, I can see, can cut through a lot of that.
Right.
And would be superior to voiceover.
Right.